Got 1 minute left. Wait, it's time. So like normal, we're going to go over it in class here. And real quick note, there's last few quizzes, there's been a couple that have not had names on them. So just double check that the name is on the first page of your quiz. And then again, yeah, you all are grading the quiz, and I'm trusting you to be honorable people and mark your own quizzes correctly. So this first problem here, just testing that we can slice lists just like we can slice, we can slice strings just like we can slice lists. Computer science tongue twister. And so the first 4 letters of hello world are just hell. So maybe this quiz was hell for you. And question is, what about the quotation marks or not quotation marks? Yeah, so I guess it's being printed out, so there's no technical quotation marks. If you added quotation marks, that's fine. If you added the O, that's not fine, but as long as you got HELL, then that's fine. Number 2, I think this was maybe the most subtle or most tricky problem on the quiz. And what it's testing, again, is that you know the types of what the indexing and slicing is going to give you, and that when you compare things of distinct types, it's possible to be true, but when you compare things of different types, you can never be true. And so here, in this case, we get true, because S is a string, XS is not a string, it's a list. But all of the things inside of XS are also strings. So S at position 1 is a string, XS at position 1 also a string. This is single quotes, this is double quotes, but that doesn't matter. Those are the same thing in Python. And so these two things are equal to each other. On the sort of second version of the quiz, there is a subtlety of using slices. If I change this to slices like this, then we would get false if this were slices. So the actual answer is true. Let me write it up here before I forget. In this case, with slices, it would be false because the slice doesn't give you the element, it gives you the list containing the element. And so we'd have a string compared to a list this way. That would be false. A string can never be equal to a list. But when we're looking at just the indexes, just the values, then a string, we would get a string, and a string can be equal to a string. So again, these are the sort of subtle things that when you're like working on your own code and programming something that might be 200 or 300 lines long, you might gloss over something like this, thinking that, oh yeah, I'm getting out just an individual character, an individual item like this. But you really have to be paying attention to these subtleties, or you're gonna waste a lot of time debugging. Okay, number 3. So our string Python is awesome. We do the replacing, but the replacing, remember, does not affect the actual string. It returns a new string. So number 3, the answer is still just Python is awesome. No, not everything is awesome. Only Python is awesome. Number 4, come back. There we go, number 4. So here we have some extra spaces inside of our Python is awesome. And, but the subtlety here is that when I do s.split, it doesn't change the value of s. It would return a list giving me the split things out. So it would return a list containing Python and is and awesome, but then we just totally discard that. We don't set it equal to a variable. And so here t equals s at position at -1. Here's our s, here's the position at -1 is the e, so it's just the e for number 4. Question is on number 3 over here, why is it still Python is awesome? And the answer is that the key principle here is that strings can never change. Once the string is set to a value, you can never change the value of that string. And so when we do s.replace, it doesn't actually modify s. It creates an entirely new string and gives us back that entirely new string. And so that's the difference. One of the differences between strings and lists in Python is that strings are immutable. You can never change them. So the only way to do a replacement is to generate an entirely new string. And the way that happened in the practice quiz was t equals, and then printing out the t's. If we do that, then that would give us everything is awesome because we're actually storing the results. But when we don't store the results, then it's like that line never happened. And that's the same principle for number 4 about what's happening here. We're calling s.split, but we're not actually doing anything with the result of that. So it's like that s.split never happens. Good question. Any other questions about things so far? Number 5. So here we have the split again, but we're actually saving it to a variable. Now the thing that we're just ignoring is this join right here. We are calling join, but we're not doing anything with it. And so when we come down to print, we're printing out the actual list of Python is awesome. If your list of Python is awesome, it looks slightly different, then that's okay. If you didn't miss the quotation marks or missing commas or something like that, that's okay. The important thing is just that there's a list and it contains Python is awesome. So again, for any of these list operations, if you're not assigning a variable to the results of the thing, it's just discarding it, you're not using it at all. Number 6, okay, so here we're doing Guido von Rossum, and we have s.find, and we're searching for the space. And there's multiple spaces in here, so find is going to give us the very first one. Gives us position 5, which is the first space. And then we're going to do a slice here from position 5 plus 1, so it's 6. So it's not including the space, but the v after the space, and print that out, and we just get von Rossum. Number 7. So when we compare things in Python, remember it's not alphabetical, it's ASCII-betical. So we look up the number corresponding to whatever is in quotation marks and compare those numbers. And so in this case, we get true that the comma is in fact less than a. Number 8. Again, so just testing the ASCII-betical comparisons here. So we have our string s, and then we split it into these 3 different words. So it'll get split like this into abab, and then we sort those. And that's the key idea, is that the sorting, the uppercase letters are going to come first, and then the lowercase letters afterwards. So if we were alphabetical, this would have come first, but since we're ASCII-betical, that comes last. So it's Abba, then was it B, something like that, maybe lower cases, and then the A. Yes?
Yeah, I got it correctly, but you said not actually. Yeah, I got it.
Right?
What if I didn't put the bracket?
Yeah, question, if you don't put the bracket, that's okay. For this problem, just as long as those things came out in the right order, then you're okay.
I have two quick questions. For number 5, if you just get the list, my phone is awesome about the comments.
That's fine.
And then also for just a background to the question, so in this you have a underscore, like the bracket underscore, and in Python tutor you put the underscore, it doesn't work at the same function.
So on the quiz itself, I don't have a, let's see, I can come back over here. We can open up the practice quiz. Anytime we print out something, in that's source code, we always put this little cup symbol here. It looks kind of like an underscore, but it's not an underscore. That's actually just a printed space. And that's how we represent that it's a space. We know that it's a space and not an underscore because there's these little upticks on it, and it's a little bit smaller too. Yeah, so that's a space. It's meant to indicate just a space.
Okay, so just in Python tutor you put.
Yep. Good questions. Any other questions so far? Okay, number 9. So this one's just looking up on your ASCII table what 10 is. The key thing to remember here, though, is that the X is for hexadecimal, and so that is the number 16 for number 9. And the last one, number 10. So again, we're looking up, but now we're going in the looking up the letters. Again, it's the \X, so it's hexadecimal. So look up the 4C, you get L, 4FO, and 4CL for a nice law to end the quiz.
Is it case sensitive?
Is what case sensitive?
The hexadecimal looking at it, because in this like chart, it's for capital C.
So the question is this case sensitive? And the answer is no. That the lowercase c and the capital C mean the same thing. This X right here, though, that would be case sensitive. If I replace that with capital X, then it would be something different. But the hex numbers are the same thing. Doesn't matter. Sorry, I can't hear you. Yeah, you feel free to write whatever you want on the quiz. And then on the front page, give me the total at the top of your quiz, and then pass them up so I get everybody's quizzes. While you're doing that, there's a file monday_section1.py that we'll be going over today in class, and feel free to bring that up on your laptop so you can follow along with how we're doing. Any other quizzes? Okay, so yeah, again, this monday_section1.py is what we'll be going over. I'll pull that up here in a second on VS Code. Let's see, yeah, so before we start going over these notes, though, I have one quick announcement about the future of this week, that tomorrow I'm supposed to go in for jury duty, so possibly, depending on how that goes, we may have to adjust what the rest of this week looks like, but I'll let you all know if anything changes. The default is that everything will happen like normal, but you might get a message on Tuesday night saying that class for Wednesday is going to be postponed or something. Okay, yeah, so today we're continuing our discussion on strings, in particular on this Unicode concept. which I briefly mentioned last time, is how the non-English characters get represented inside of computers. And that'll be what we're focusing on today. And then on Wednesday, we'll be talking about files, how you load and open files on computers, and how that interacts with this Unicode system. Let's see, so one of the things that Python is famous for is that it has really good Unicode support. So Python became first popular in the 1990s, and at that time, there were no programming languages where it was easy to have non-English stuff going on in your computer code. C, C++, Java, those are other languages that you might have heard of. It's relatively difficult to do things correctly in those languages compared to Python. Python, we'll see that it's not easy. There's still a lot of things that you have to think about, but it is in some sense as easy as is possible. It's just a complicated thing. You might have also heard that there's so right now we're on Python version 3, there's this older Python version 2, and there's actually still people, so Python version 2 is officially what we call end of life. It no longer has support. Guido said, you're a bad person if you're using it still. But there's still millions of people who are using it because Python 2 and Python 3 have different philosophies on Unicode. And this is a big debate in the Python community. And if you are, let's see, the sort of person who is interested in potentially a long-term career in computer science, these sorts of debates are things that you should be aware of. And so I'd recommend reading this. But it's not going to be part of the class at all. And then the last thing, all the information that we're talking about today is not in the textbook. It's actually not traditionally a part of any computer science curriculum. So this is something different that this class has that, say, the Pomona or the MUD students don't have. And the academic reasoning why those departments don't have that is because this is sort of not a computer science topic. This is like a people topic and difficulties about relating to people. And so they don't like teaching it. But companies always complain that, you go to Facebook, Facebook is not just for Americans, it's for people all around the world. Similarly, Microsoft products and really any company these days has to support people around the world. And so companies are always complaining that people don't know how to do that. And that's one reason why we're including it in this class, that it's actually important in the real world. But another reason is that for the data science majors, if you're going to say analyze data, a lot of data comes in non-English things, non-English forms, and so it's particularly important for data science majors to understand the stuff that we're talking about today. So all that said, your actual reference, your actual textbook is this link right here. If you click on it, it'll take you to this webpage that is going to explain everything we're talking about today, just maybe in more detail. So that's what you can reference if you have questions. Any questions before we get started? Okay, I have a lot of non-technical links down here that we'll look at in a little bit, but we're going to start diving into the sort of technical issues. So I have VS Code open now, and this is our Monday_section1.py file again. And what I'm going to do is down here on the bottom, I'm going to just open up my interactive Python. So again, Python 3, here's the name of the file on the right, and the -i in between means it's interactive. So I'll get to interact with all of these variables that I'm defining up here. And whoops. I apologize for this. I have a typo in my thing, so it's not loading. And it's on line 80, so let's just comment that out for a second until we get there. And come back up to the top. Leave that, and back into Monday section1.py. So the particular file that's on GitHub right now is this same file. And when I loaded it, we got this error right here. We'll see what that error message means when we get to line 80. This is the line that it's happening on. I just commented out line 80 in order for us to be able to load it and start looking at this file. So the very first part of this, this file has just a bunch of different languages, and you can see that they're all inside of Python strings, and they're mostly going to do what we would expect them to do. If I come down here and type the English, then I'm going to get English text out here. If I type Chinese, I get the Chinese text, and so on. And so the first sort of takeaway from this is that like things seem to do what you want. You can just put foreign language text inside of strings, and it's mostly going to work. If you're not like super familiar with a lot of these languages, some of this might surprise you. So like this Arabic is written from right to left instead of left to right. And so you can see where my cursor is over here with Arabic. I'm going to just hit the right arrow on my keyboard, and you can see suddenly the cursor jumps all the way over to the right. And now I'm still hitting the right arrow, but my cursor is actually moving to the left. And then as soon as I get over here, it jumps back over to the normal position where I can type things normally. So because Arabic is written right to left, everything suddenly becomes backward when you're inside Arabic text, but when you're not inside of Arabic text, everything is normal. That's not something that's going to necessarily, you don't have to memorize all the languages with backwards or right to left text instead of left to right text, but if your keyboard is behaving weirdly, then that's one likely problem. Lauren.
I have a question about the terminal. So you type Python 3-I.
Mm-hmm.
Is it the same thing as IPython?
This is a good question. Here, or the question is, I have this -I here next to Python 3. Is this the same thing, or is it related to IPython? And the answer is no, that IPython is something that happens through the web browser. And so I think actually in CS5 at MUD, they might be using IPython for some of their assignments. But this is different. Both of the I's happen to stand for interactive, but they're not really related to each other. Yeah, you go.
When we have like the languages that go from right to left,
Mm-hmm.
does it change anything about indexing?
About what?
Indexing.
Oh, good question. The question is, does this change anything about indexing? And technically no, but it might seem like yes. And here, so it's gonna, in this particular example, Arabic's really hard to demonstrate this with, because an individual character, when it's written by itself, looks different in Arabic than when it's like written with other things. It's all like cursive-y, so there's different forms, whether the character's by itself, at the beginning of a word, at the end of a word, in the middle of a word. So we can't really demonstrate this. Well, let's see. We'll see in detail here in a bit how the indexing works, and that will hopefully clarify that question. But that's a good place for your mind to be going. Try.
When I put Arabic into my terminal, I'm getting the Arabic text in the middle, but with some, it's like \U2.
Yeah, so this is a good question. The question is that here we have all of these, on my computer, all of these symbols are being displayed properly. On your computer, that may or may not be happening depending on what fonts you have installed. So I have fonts for basically every language installed on my computer. If you have only, if you don't have that, which most of you probably don't, then you might get some weird symbols appearing here. And that's okay, that's expected. Ready?
Just a question, why does Arabic 1 return the Unicode?
It's a good question. The question is Arabic 1 right here, why is that actually giving this instead of a symbol? And that's great question. We're not at a place yet to answer that. There's a lot of subtle things that we'll get to here in a second. The main thing at this point is just that it is possible to put foreign languages inside of strings, and at least at a first glance, it seems to work correctly. But you've all raised excellent issues about subtleties, about how it's not just, we need to look deeper to answer all of these questions. So lots of great questions, hold on to them, and we'll see if we answer them here today. So yeah, you can store text, foreign language things inside of strings, and you can combine foreign languages together. It works totally normal, again, except with this weird behavior of Arabic or other Hebrew, other things that go in the opposite direction. You can get the weird behavior, but that's actually what it's supposed to do. You can also create variables that are non-English variables in Python. So here, this is Korean for computer. So this is just my variable, and I'm assigning it to this string, and that's totally okay. If I copy and paste this down here, then it's assigned to this value. This is a variable. Even people who program in foreign languages typically don't do this, though. You'd 99% of the time have all of your variables still be in Latin characters, even if you're like a native Korean speaker and don't even speak English at all. You'd still use Latin characters for your variable names. And emojis also work fine. So here's just a smiley face emoji. This one down here is actually the poop emoji, but I don't have that font installed on my computer, so I get this square box. So that's one of the things that can happen if you don't have all of the fonts installed. And now I want to talk about just some weird things about languages that we're going to have to deal with. So here, this funny bee-looking thing is a German character. And if we take this German string, Strauss, and German.lower like that, then lowercasing it does what you might expect. That this capital S right here gets converted down into this lowercase s, and yeah, that's what we would expect. But now if I do German.upper, things don't quite behave how you might expect, that this one character converts itself into two characters. This is the lowercase letter in the German language that has no sort of uppercase equivalent. That is a single character. The uppercase equivalent is actually two characters. And so if I ask for what's the length of this German string and the length of the uppercase version of this German string, we actually get different results. And so in English, if you have a string and you make it lowercase or make it uppercase, the length of that string is always going to be the same. But that is not true in every language, and so that's something that you can't actually count on in Python. Another thing that's weird is, so numbers. Here, this looks like an 89 to us maybe English speakers, but actually in the Tamil language, this 8-looking thing is how you write the number 4, and this 9-looking thing is how you write the number 7. And so if I take numbers down here and convert it into an integer, I actually get the number 47 and not the number 89. If I converted, so 89 gives me the number 89, but numbers with this 8 and this 9 weird looking thing here give us the number 47. And it turns out that there are lots of different languages that all represent numbers different ways, and all of those are supported inside of Unicode. And some of them just have this sort of confusion that they look similar to other systems, but Unicode still behaves properly. The next thing that's weird here, so we have URL1, URL2, and URL3, all to bankofamerica.com. So you might, this might be a bank that some of you work with, but actually all three of these URLs are different from each other. If I do URL1 equals URL2, we get false. And if I do URL2 equals URL3, we get false. The reason for that is because, so this one up here is written in actual English characters, Latin characters. This one down here is actually written in Greek characters. And so if I take this alpha right here, this alpha, and I uppercase it, the upper, I get, this is an uppercase alpha, but it looks like an uppercase A to English readers. And so if I type this in on my computer, I actually go to a totally different website than Bank of America. And even though it looks like Bank of America, it's not Bank of America, it's Bank of Alpha America. And so this is a common way for, say, spammers to try to impersonate other websites or impersonate people like user accounts on different social media forums to find characters that look the same as other characters, but they're actually not the same. What's happening in this one down here, number 3, this is actually all English characters, but there's this special character in Unicode called the empty character that takes up no space. And so I've just included a couple of these empty characters up here, and and it takes up no space, so you can't see it, but it's there, and so it represents a different string. And so if I did the length of URL1 and the length of URL3, spelled correctly, we see that the length of URL3 is 30, the length of URL1 is 29, and that's because there's these empty characters inside of here. If we look at this empty string right here, it looks like there's nothing in this empty string, but if I come down here and do the length of empty, there's actually 42 characters inside of this empty string right here. You just can't see them because they don't get printed. There's no, I would say there's no picture that corresponds to those characters. And so this is just a small amount of the weird stuff that can happen in languages. And a lot of the stuff that we'll be talking about today is how do you like write code that's actually going to be able to do reasonable things in all of these situations. Any questions so far? Yes. No.
No.
Yep.
Could you just go over again why the URL?
Sure. So the question is, why exactly are these 3 URLs different? In this case, this is what it's supposed to be. These are the actual American characters, Latin characters, English characters. This one down here, it looks the same as this one up here, but this A is actually a different A. It is the Greek alpha. And so if I do ORD, remember ORD gives us the number associated with a letter. I get 913 for that one. And down here, oops, for the first one, copy and paste that A, I get 65. So they both display the same, but they have different numbers that represent them, and so that's why they're not equal to each other. This one down here, it's all Latin letters, but there's extra characters that I've added to it that just don't get displayed at all. These empty characters, like down here.
So how will we be able to?
Yeah, great question. So the question is, how can you tell like these 3 things, they should be equal to each other, but they're not equal to each other? How can we tell that? And that's one of the things that we'll cover. We're just raising all of these issues at this point, letting you know why text is a lot more complicated than you think it maybe should be. And let's see, since we're talking about these URLs right now, let's talk about, so the NSA has a security risks of Unicode document right here that anybody who works for the federal government on like information systems has to read this and understand it. But this gives you an overview of techniques that you can use to like impersonate other people or impersonate web pages online using Unicode and these characters that look different but are actually the same, or look the same but are actually different.
So that's identifying the issues or teaching people how to hack?
So the question is that identifying issues or teaching people how to hack? And in some sense, there's no difference between the two. That if you know, like, this is the security vulnerability, this is the way that somebody can impersonate the real Donald Trump online, then you know how to do that. If you know how to stop it, you know how to do it. If you know how to do it, you know how to stop it. There's sort of no difference between the two. Okay, so this is all the issues. Now we're going to dive into the like technical details about what's going on concretely. So the first thing that we're going to talk about is something called code points. And in order to do that, we have some background definitions, and this first one is a grapheme. So a grapheme is what Unicode calls one of these like individual units of text. It's what other people might call a letter or a symbol or a character. I'm not using these terms because they have their own, so they're in quotation marks, like scare quotes, because these have their own technical definitions inside of Unicode. But a grapheme is just like the thing that's actually being displayed. So this alpha, this A, they have the same or similar graphemes, but they're actually different letters. And a font is what is a set of pictures associated with each grapheme. Yeah. So let me clarify what I said before. This A right here is a different grapheme than this A right here. These two A's are different graphemes because this one is the Greek alpha grapheme. This one is the Latin A grapheme, but they happen to have the same picture representing them on my installed fonts. For other installed fonts, those pictures will look different, and so things will look different. But for the installed fonts that I have, they happen to look the same. One of the recommendations in that NSA document is that there's a certain set of security-aware fonts that make all of these like A's distinct from each other somehow. So if you're using the Greek A, it looks different than the Latin A. And so that's their recommended best practice for government systems, but then it also makes like Greek text look weird because then the A is gonna be kind of funky looking, but necessary for security in some sense. So that's what a grapheme and a font are. And a code point, let's see. So each grapheme can be composed of one or more characters. And a character is the actual fundamental like unit of Unicode. And the same grapheme can be written in different ways. So here we have accents 1, accents 2. These two things are actually the same grapheme, the same A accent mark. But if I compare them, accents 1 equals accents 2, we get false. And the reason is because they're represented using different characters. So this is the same grapheme, different characters. If I do the length of accents 1 and the length of accents 2, we get different numbers here. So the length function displays the number of characters, not the number of graphemes. And then equality in Python is always done on a, is not done on a grapheme equivalent, which is what you might want, but it's done on character equivalents. So these two things, different character representations, and so not equal to each other. So now we need to talk about like how do you actually get what are the underlying character representations of the graphemes that you're looking at. And that's what this section down here is going to illustrate for us. In order to just first illustrate that these are in fact different characters representing the same grapheme, we're going to look at some different ways that we can input the same character into Python. So we've already seen the \x notation. \x means the thing after it is a number, and that's the number that represents the that particular character. The \x has range from 0 to 255 because there's just, you can only have 2 letters after it, 2 hexadecimal numbers. If you need a number bigger than that, the \lowercase u has range from 0 to 65535. And the \uppercase u can store anything. And the reason these ranges are different is because \x, you have to have exactly 2 hexadecimal numbers, \lowercase u, exactly 4 hexadecimal numbers, \uppercase u, exactly 8 hexadecimal numbers. And here, we can always represent these things. Anything that's represented by \x can always be represented by \u using, just by putting zeros out in front. And similarly, by putting more zeros out in front, we can do the \uppercase u. So these are all equivalent. If I do down here, accents_1 equals accents_1a, we get true, 1b, C, true. All of these things are equal to each other. They're just different ways of entering it in Python. And if I were to print out accents 1b, for example, or 1a, or 1c, it's not going to print out this underlying representation that I used to enter it. It's going to print out the actual grapheme down below.
So this is like the picture is different, but the grapheme is the same.
All of these, both the characters and the grapheme are the same for all accents 1 variables. The thing that's different is I'm using a different notation to enter it. But the character and grapheme is the same. Just notation is different. The different, yeah, all right.
What makes the accents 1 and 2 different?
So yeah, the question is now what makes the accents 1 and 2 different from each other? So accents 1 1A, 1B, 1C all have the same character, same grapheme, different notation. Accents 2 has same grapheme, different characters. There's 2 characters inside of the accents 2B and 2C and 2 up here. The first character is the letter A, and then the second character is something that we can't really pronounce. It just says add an accent mark onto whatever came previously. So this A like that gets displayed as a accent mark because this \U0301 means just put an accent mark on whatever came previously. If I put an E right here, we get an accent on that E. Something that most languages don't have is a Z accent mark like this. I don't think there's any language that uses this thing right here, but we can construct it this way. We can construct it by saying whatever character we want, put an accent mark on it with this. And so this is 2 characters, this add an accent character and the Z character, but 1 grapheme. And so because up here, I just had a single character, which was the A accent mark character, and down here I had the A character followed by the add an accent mark to it character. It's 2 different characters, but it represents the same accent, the same grapheme.
Basically just switch format of character, but it prints on the same that it uses different.
They will both print out the same thing. But we want to be careful with that print word because the print verb implies fonts, and we're not able to talk about fonts yet. We're just talking about characters and graphemes. Okay. Question is, can you have negative ranges in any of these? And the answer is no. They always start with 0 and go up to whatever the max is that can be stored. I guess I didn't write out the max here. So from 0 to it's about 3 billion, about 4 billion. And that happens to encompass all possible characters that exist. Question?
Yes. 2B and C have the same length, and
so accents 2B and 2C are the same, which also implies that they have the same length. So one thing to note here is that I don't have an accents 2A because it's impossible to use the \x notation to write this character right here. The \x only supports putting 2 hexadecimal numbers, so decimal 0 to 255. I need 3 hexadecimal digits to write this character, and so it has to be \U, lowercase or uppercase, to write it. So now, an important question is, like, accents 1 and accents 2 really should be equal to each other. Like, how do I make that happen? And there's this idea called normalization in Unicode, which lets you convert between different character representations of the same grapheme. There's 2 of these forms that we're going to look at: normal form composed and normal form decomposed, NFC and NFD. If we do, so in order to do this, we need to do import Unicode data like this. And then if I have Unicode data.normalize NFC, comma, accents _1, that converts it into this NFC form. Composed means that whenever there exists a individual character to represent a grapheme, it's always going to represent it with just the individual character. Composed always use the smallest number of characters possible to represent it. Decomposed means it'll use the largest number of characters possible to represent it. So it turns out that accents 1 happens to already be in NFC form. So this gives us this function right here converts into NFC form, converts accents 1 into NFC form. But again, it doesn't modify accents 1 because you can't modify strings in Python. It returns a new string that is in NFC form. And it also turns out that accents2 is in NFD form. So I'm going to, in order to demonstrate that, I'm going to convert accents1 into NFD form. Again, the D stands for decomposed. So take the individual character, break it out into multiple characters, and we'll check to see is that equal to accents2, and it is in fact equal to each other. So accents1 equals accents2 if we first transform it using the normalization. So there's a couple other examples that we'll look at here in a second, but this gives us our first principle of working with foreign language or strings in general in Python, is that you must normalize your strings if you want to compare them. It doesn't matter which normal form you use in your application, whether it's NFD or NFC, you just have to pick one and use it everywhere and make sure that as soon as you get a string in, you always normalize it so that you can do that comparison in the normalized form. Typically, people use the NFC form because it's fewer characters, but it doesn't matter which one you use. See, so another example, we have Vietnamese here, and Vietnamese is sort of like Latin-looking language, but there's lots and lots of different accent marks on Vietnamese. And so if we look at the length of Vietnamese, NFKD, and NFKC, we can see that there's a difference in 10 characters between these two forms right here. But if I were to normalize them both, then I could compare them for equality. So Vietnamese underscore NFKD equals Vietnamese underscore NFKC is false. But if I normalize them both, Unicode data dot normalize NFC of that, Unicode data dot normalize NFC of that, then we get true because we've converted them both into NFC form. And just by looking at it, we can see that they're the same graphemes. And so in order to actually check grapheme equality, you normalize and then you can check, and then the equality will be grapheme equality. Any questions about that? Ready?
In the first previous one, accent on the short three. What is ANKC?
Yeah, so here I have NFKD, NFKC. Oh, and my typo right here, NKC, this was supposed to be NFC. NKC is not a thing. That's why I was getting the error message. If you type in try to normalize something, but you have something in here that's not a valid normal form, you'll get an error message. And so there are other normal forms besides NFC and NFD inside of Unicode that do different conversions, but these are the two most important. So that's the only ones that we'll cover in class. Let's see, another example here is Arabic. So there's some really weird characters inside of Unicode, and I just mean weird from like a linguistic sense or a computer science sense. But so here, this PBUH stands for peace be upon him. So it's a common thing for Muslims to say related to the Prophet Muhammad. And they actually have just an individual character, an individual grapheme that represents this. And so this is just one word, one letter right here that represents sort of this whole sentence. This one right here is the longest character in all of Unicode, the basmala, which when translated is roughly in the name of Allah. So it's just a single character that represents the entire clause of a sentence. And with different normal forms, these things, you can transform them to be different things. We can decompose this. So basmala, Unicode data dot normalize NFD basmala like this, and this is happens to be the decomposed form. Another decomposed form, NFKD, we can't really see the differences here between these because they all get displayed the same because they're all the same grapheme, but all of these are going to have different lengths. So again, the principle, you must normalize your string if you want to compare them. Next example, Korean. So this one, we're going to talk about how sorting works in these non-English languages. So if you recall, for English, we did ASCII-betically, just like that chart that you have. And for non-English languages, we'd say we sort Unicode-betically. But that doesn't sound as cool as ASCII-betically, so people will still say that we sort ASCII-betically, even for non-English languages. And so if we take, for example, so here's some Korean letters right here. If we take this one, we can get the Unicode code point that represents that letter. So the number that represents that letter like this. And that's just the number that represents this letter. And if we were to just get the numbers for all of these letters, it looks something like this. And so these are actually the first few letters in the South Korean alphabet. And so if you order things in Unicode and it contains Korean text, it will be ordered the way that South Koreans order their strings. But for various reasons, in North Korea, they have a different alphabetical ordering of their alphabet. And their principle is that this was the original, like, historic ordering of the alphabet. And so that's what they use in the DPRK. Whereas the ROK, for various reasons, changed their alphabet to be like this, to be more compatible with the outside world. And so if anytime sorting happens and you're in North Korea, you're always going to get things that are just sorted incorrectly for your particular locale, your language area. And there are a lot of other alphabets in computer science in Unicode that have the same problem. So a lot of Eastern European alphabets that all say use Cyrillic, the Russian alphabet, they might be ordered differently depending on which country you're actually from. Similarly, a lot of the Danish, Norse sort of alphabets can have different orderings depending on which country you're in. And Unicode just ignores all of that. It says, I don't care what country you're from. I don't care what your actual, like, alphabetical order is. And so it's always going to order it Unicode-betically or ASCII-betically. And if you want correct ordering for, like, that person's actual, what they think of as correct rather than what the numbers think of as correct is, then you have to, you need somehow extra information about the user in order to do that. So it's impossible to sort correctly in any programming language unless you also know extra meta information about the user. Any questions about that? Okay. If things seem simple so far, then you're in luck because now is when it gets complicated. So if things seem complicated, then now's the time to, like, really double your paying attention. So far, all we've talked about is how are strings represented in Unicode. There's these code points, which are the abstract numbers. This abstract number in Platonic math world that's never actually used anywhere, but this is the number that represents this character. Now, how do we actually store that number on the computer? That's what encodings are about. How do you actually store the information physically on the computer? And in order to talk about this, some quick background. So a bit is just a 0 or a 1. And so anytime you're talking about binary numbers, you're talking about 0 and 1, so you're talking about a sequence of bits. And then a byte is 8 bits. And for various historical reasons, a byte has become sort of the fundamental unit of, like, information in computer science. So a gigabyte is about 1 billion bytes. And megabyte, kilobyte, and so on. One of the reasons why 8 bits became, like, the standard as the fundamental unit of storage is because 8 bits is just large enough to store an ASCII value, so to store the English characters. And so if we counted how many English characters there was in a file, that's equivalent to counting how many bytes it takes to store that file.
Can you, what, 8 bits became?
So historical tidbit is that 8 bits became the standard. So 1 byte, 8 bits became the standard size that we measure because that's just big enough to store the ASCII values. And so if we have a document with 100 or 1,000 English characters, that means 1,000 ASCII values, which is 1,000 bytes to store it. So that's sort of, there's some other like good technical reasons why 8 is a nice number to work with, but this is like the fundamental social reason how bytes became important is because of ASCII. They're just big enough to represent ASCII.
Do you always store an ASCII value with 8 bits, or can, like, in theory, could you just do fewer than 8 bits?
The question is, do you always store an ASCII value with exactly 8 bits, or is there a theoretical way that you could shrink it? And there are many ways that you can shrink that. They all basically somehow boil down to compression of compressing text. So if you put things like in a zip file to compress it before, then essentially what that's doing is that's finding some other way of representing these ASCII values that's smaller. We're not going to talk in detail about like techniques for how to do that though, but it is possible in principle. Okay, so in Python there's this special type called a byte, and it looks like a string, but it starts with a B. So far we've seen like there's normal strings that just have quotes, and we've seen raw strings, quotes that start with R. And normal strings and raw strings are the same type. You can compare them to each other, and they can be equal to each other. So if we have like test equals R, test like that, we get true. This B though means something totally different. It means we're bytes now and not a string. And so if I change this right here to a B, we'll get false. So bytes are totally different than strings, even though they look like they might be related. And they are related, but they're different.
So what is the raw string?
So the raw string, we talked about that in previous class about like if you have \n in there, the \n is actually a backslash and an in the raw string. Here the \n is a new line. So the raw string ignores escape characters. And so a byte, it's actually a sequence of like actual bytes, these 8-bit like elements, these numbers between 0 and 255. And every time you load something up from a file on a computer, it's always going to come back as bytes. Every time you load a file in Python, you are always reading bytes, because that's actually how it's stored. It's stored as bytes physically on your hard drive or CD, whatever your storage media is, it's physically stored as bytes. And so that's what you're reading in from Python. Unfortunately, bytes cannot store the non-ASCII values, non-English characters. They're just not big enough. There's only 0 to 255, and there's just like, say Chinese, there's a lot more than 255 characters, so you can't possibly represent everything inside of bytes. And so this B is only for English. If you're doing something other than English, you definitely can't be using this B by itself. If we try to do that, so here I have this Korean string, and I put the B out in front, we get the syntax error, bytes can only contain ASCII character literals. And we know what ASCII is, it's anything on that big table, so anything on that big table is allowed. Korean is not on that big table, so it's not allowed. So in order to store non-English text, we need something called an encoding, which maps between bytes and characters. So again, anytime you're storing something actually on the hard drive, it's being stored as bytes. But when you're loading it, it might contain non-English things, and we have to convert it out of bytes into strings. And this encoding is how we do that. So .encode and .decode. Here we have so a string like this, .encode UTF-8 converts it into bytes. So that gives me my bytes1 variable. Bytes1 is hello world in bytes. In order to go back to a string variable, bytes1 dot decode UTF-8 like this, and it gets me back to my string. If we encode something, so UTF-8, anytime we do this encode, we have to supply a formula for doing the mapping between strings to bytes. How are we going to worry about these characters that take up more than 1 byte? And there's lots of different formulas for doing that. Here are just 5 of them, but there's literally thousands of them in existence. And depending on which one of these encodings we do, we'll get different bytes out. So here I'm going to do hello world.encode with UTF-16, and you can see that this does not look like hello world anymore. We know that this \xff, \xfe, these represent different letters because we've seen this \x notation before. These 2 letters right here represent the number that corresponds to this particular character, but it's no longer easily human readable. In order to get the actual hello world back, so that's still bytes 2, in order to get back bytes 2, I decode, and I must specify the same exact string right here that I used to encode. So since bytes 2 was created with UTF-16, it must be decoded with UTF-16 as well. If I ever use the wrong encoding, I'm going to get something that just looks like gibberish out. So bytes1 was created with UTF-16. If I do bytes1.decode bytes1 was created with UTF-8. If I decode with UTF-16, we'll get an error message, in this case, that it just doesn't work. There's no, the mapping that you have, the variables that you have are invalid.
What if it can't contain the extra pieces of code?
Sorry, can you say that again?
Because like 16 is more than 8, and so if you encoded with 16, or you encoded with 8, it doesn't have enough space, or just like it wouldn't. It would just be like if you're trying to. Would that be similar to like you mix up hex and like an octa whatever language, octa language, where it's just like different indexes kind of thing, or different.
Yeah, so that's a good analogy. Like each one of these, like one of these is like binary, one of these is like octal, one of these is like hex, and so if you are using the wrong one, you'll get the wrong value when you come out to decimal.
Okay.
But yeah, so like the number 10110, that can be binary, octal, or hex, but the number FFFF, that can only be hex.
Okay.
So principle number 3, whenever you're working with bytes, so whenever you're working with files, like we'll see next time, you must know some meta information about the encoding, like what is the actual encoding? Which one of these things should I use? Which one was it created with? If you don't know that, you won't be able to open the file. All of these things work with any language besides English. So here's Chinese. If we look at Chinese bytes, then this is what the bytes is of UTF-8, and it just looks different depending on which one of these you happen to encode with. The length of any bytes gives you the total number of bytes, so it gives you the total amount of disk space that you're going to use. And so the reason why you might choose one encoding over the other is because certain encodings use less disk space than other encodings for different languages. Just so happens that UTF-16 is the best one for Chinese, and UTF-8 is the best one for English. And so there's been sort of this power struggle on the internet between which encoding is going to become the dominant encoding. That the English-speaking world always uses UTF-8 because it uses the least amount of bandwidth and disk space. The Asian world always uses UTF-16 because it's the most efficient for them. And they're a little bit annoyed that everybody's kind of switching over to UTF-8 at this point. Let's see, that's pretty much all the time that we have today. So for next time, we've pretty much finished our discussion of Unicode by itself, but we'll see how this actually applies, loading and writing files. And all this background information will be needed then. Happy to stick around and answer questions. And I also have my office hours now. So yeah, see you all either on Wednesday or right now for questions.
Does the length function return the number of bytes?
Exactly.
Bits or bytes?
Bytes.
And you multiply that by 8, you get bits.
Yep.
Is there a way that you could change, like in the bottom right corner of this thing, it says UTF-8? Can you change that to the UTF-16 if you were working in Chinese? For example?
So Python 2, you can use any encoding scheme. Python 3 forces you to use UTF-8, and so that's one of the reasons why a lot of people haven't switched from 2 to 3 is because they want to use UTF-16. But you can't.
I might ask a really quick
Go
question.
ahead.
I got it right on the quiz, but I haven't but I think I interpreted it in the wrong way, in a different way than you did. So I know that you have to have a variable for the function, right? For replace, or stuff like that.
Yep.
But that is also for a list.
It is
No.
raw.
No. It can do it, but
List functions will modify the list.
yeah.
String functions will not modify the list.
Yeah, exactly. So this one, in order for this to work, it has to be a list, right?
Well, the replace doesn't exist for lists. So even if it was a list, then it would be an error because
Okay. So that replace is to replace something with something, right? But if it's a list, it won't modify. No, sorry, a string, it won't be modified. But for it to convert it into like a split, and then it will work.
you can't call replace on a list.
Okay, then when will replace work?
I think you want to take the verb work out of your vocabulary because it's a little bit ambiguous. Because replace always works.
Wait, okay,
So what it does is different than what you want it to do. Replace returns something.
Right.
So we have s dot
Replace.
whatever it is. This variable is not modified, but this puts something into this t variable. If now at the end we had print t,
Yeah.
then
And that will be
it would
good.
show the replace, but we have to print s.
But even though it's a string,
Yeah, it doesn't modify the s, it gives us a new thing.
gotcha, so the t, but it will be modified. Okay, so the s will not be modified, but however, when it modify replace, but it will be modified to t.
And the idea is correct, but the verb modify is incorrect.
Okay.
It's a new variable.
It's a new variable, so we just take the string over and then put it into something else. So okay, I'll understand that. All right, I'm lucky on okay. So and for the list, so why does sort need not a place? So why does sort need a variable?
What do you mean new variable?
Like you can just say, let's say pass this the list, right? Why does it need a variable for the sort?
You're saying that
Sort,
Um,
which is
So-
passive.
I would, again, the verb need, I want to just be more careful here, that it does need a variable, it needs a variable here.
Oh no, it's a sign of a variable. Why do
Right.
you need to assign a variable?
So lists, if you have something to write the dot, it modifies it.
It modifies it so it's just directly that.
Yeah.
Nice. Okay.
All right. So that's the difference.
between the list and the string is the list you have to do the equals. So the string you have to do the equals, the list you can't do the equals.
Gotcha. Thank you. Who's gonna make an office hour today?
I have office hours right now.
Oh, okay.
Yeah.
As you could tell, I messed up and overslept. Is there any way I can make up for the quiz?
We'll have some makeup opportunities later in the semester, but yeah, unfortunately not for the.
Or make up, as in like, would it be extra credit or an extra quiz or something of that nature? Or what those opportunities look like?
It's going to be that we'll have a bigger quiz here in a week or two that'll replace, count as that quiz plus replace the loads of a previous quiz. So
Okay.
replace the next quiz.
What are Chinese bites?
What about it?
What are Chinese?
It does sound funny like that.
I was wondering, I said to Chinese students, when they